thank you very much for giving me this opportunity to report some measurements we did with our target simulator. For those of you who are not familiar with target generation technology, this is just a very brief slide. So instead of using a real radar target like a sphere or a corner reflector, we're generating a virtual target by placing the target simulator. You can see on the right, somewhere in the field of view of the radar. And so we receive all the radar pulses, and after a given time, we retransmit these pulses with a certain amplitude and phase. So we have full control over the delay, the phase, and the amplitude, and so we can generate a virtual target with arbitrary size and Doppler speed, and also at an arbitrary range gate. So in this talk, I will talk about two experiments we did 2 months ago. So one experiment was taking place at the CSU Chill radar facility in Colorado. There we were investigating the Chill H-band radar. I think it's a very famous radar. It's an S and an H-band radar. We were only looking at the H-band frequencies. The most prominent feature of this radar is the 0.3 degree beam width, which imposes some difficulties for the calibration. Also at the Chill radar facility, there was the RX-725 radar, which is actually a similar design than Chill. So it's the same signal processor and same transmitter, but it's a conventional dual pole antenna. And then the third radar we were investigating was the Peaks 1000 from the Advanced Radar Research Center of the University of Oklahoma. It's a solid-state radar that uses two individual 200-watt transmitters. And because of this unique transmitter design, it's very frequency agile, and you have full polarimetric control on the transmitted waves, and this will be used for the determination of the differential phase on transmission. There are also some additional measurements. Not all of those I have already used for my analysis. So for example, in Colorado, they were doing a sphere calibration with a sphere that was lifted by a drone. But I do not have the results yet. But there will be some comparisons with the sphere calibrations and our target simulator measurement. In Oklahoma, the people were using horn antennas and power meters to measure the transmission, the differential phase of the Peaks 1000 radars, and I will talk about this later in this talk. So let's go to the first radar, which is the small X-band radar at the Chill facility. We were placing our target simulator on a lifting platform as shown here at a distance of about 400 meters to the radar. The radar was performing 26 PPI scans in the direction of the target simulator. And you can see the amplitudes of the pulses as received by the target simulator here. So this is the pattern that was recorded of one complete box scan around the target simulator. And then we were generating a target, or actually several targets, but I'm showing now just one. So these are the polarimetric variables and also the Doppler measurements of the radar. So we were generating a 39 dBz target with 0 dB differential reflectivity and 5 meters per second velocity. And it actually, they look quite good, I think. There is this prominent feature here. So this edge, which is due to our internal self-calibration of the instrument. So during self-calibration, the radar, our instrument is not transmitting anymore. So the radar is not receiving anything. There is a little bit of clutter down here, and this is actually very well represented in the copolar correlation, which drops down quite dramatically in this region, but not only the copolar correlation, but also the spectral width. So if I zoom into the reflectivity measurements, this is what you can see here. You see a very nice Gaussian shape, and the maximum of this Gaussian shape is at 37 dBz, and what we have generated is 39 dBz, so there is an offset of 2 dB. There are a couple of reasons that are currently being investigated. There was also a range offset, that the pulse width that was transmitted was not exactly as it should have been, so these are some reasons for the 2 dB offset. So this is the differential reflectivity, and I just like to show this plot here because I think it's quite interesting to see that where the ZR approach is 0 dB, this is really at the center of this Gaussian beam, or at the maximum of the power of the reflectivity. And the offset I have here is 0.5 dB. So these were already the data of the small X-band radar. Now we go to the large X-band radar, which is the chill radar. We were using the same platform that were used for the small radar, but the scan strategy was a little bit different. So chill was scanning, was performing 6 PPIs in the direction of the target simulator. So it was doing PPIs like this. This is actually PPI animation of the force elevation, so at 0.7 degrees. The target was generated at 18 kilometers. And what you can already see here in this PPI animation is that it's quite stable. So it really remains very choppy. When we do a vertical cut through this range state, and this is what we see here, and so the most obvious feature is this shift from one PPI to the other, and this is actually a gear backlash of the chill radar, which is about 0.15 degrees. However, for the upcoming analysis, we are looking just at this PPI elevation here, and I was performing Gaussian fits on this data and then extracting the respective polarimetric variables, and doing plotting some time series. So this is the time series, the 1 hour time series of the reflectivity. So the blue dots are the radar measurements, and actually the red line is the reflectivity that we have generated with our target simulator. So a part of the nice agreement, I think the most striking feature and something so people that are attending online, can you switch off your microphone? Thanks. So yeah, so the amazing feature here, I think, is the stability of this reflectivity. So I try to express this with this figure down here. There is also quite a nice stability in the ZR measurements, but with the ZR measurements, we have an offset of minus 1.4 dB. I don't know currently where this offset is coming from. It might be a far field effect because this is a huge antenna. The far field is very, very far away. Our measurements were taken at 500 meters, so there need to be, yeah, we need some antenna specialists to decide what this could be, what the influence of this could be. So now let's go to some other time series, like the Doppler velocity, for example. It's very accurate at 5 meters per second. So we were generating 5 meters per second. The radar is seeing 5 meters per second. So everybody is happy. Also for the copolar correlation, we assume a very high value of 0.996. I think this value could be higher, but I'm not 100% sure about this. So it probably could also be a near field effect. And then the last two time series I'd like to show, this is the phi dp and the spectral width. So the absolute value of the phi dp is not of any importance here because I was transmitting with an arbitrary phase shift, but I just wanted to show the stability here with a sigma of 1 degree, which I think is quite good for an X-band radar. And then last but not least, the spectral width, which is actually a measurement of the phase noise of the radar transmitter and the radar receiver, but also the phase noise of our instrument. So in the future, I think we can use this measurement for assessing phase noise, but for the moment, I'm just giving these measurements as they are. Okay, this is the office dog here. Sorry for that. So last radar we're measuring, which is the radar in Oklahoma. The radar is located here, and our target simulator is on a tower at a distance of about 200 meters. The radar was performing RHI scans around the target simulator, but it was also performing stair mode observations for the phase measurements. So we also did the calibration measurements with the Peaks 1000. This is a real-time display actually, or just a photo of the GUI they were using there in Oklahoma. We're generating a 60 dBz target with minus 10 meters per second Doppler velocity and 0 dB differential reflectivity. And I just did some quick statistics here. You can see the figures. I think agreement with the reflectivity is quite good. It's a bit worse with the differential reflectivity, and for OHV and velocity is quite accurate. But what you also can see is the standard deviation is is higher than for the chill radar, and there are various reasons for this. I think one reason is that there were some problems with the pointing of the antenna in Oklahoma. But actually, the main focus of the campaign in Oklahoma was not the calibration of the reflectivity, but actually we were interested in the determination of the differential phase on transmission. And those of you who have attended the AMS Radar conference in August probably have already seen some of these figures, but yeah, sorry for that, but I will just quickly repeat some of these explanations. So the Peaks 1000 has two independent transmitters, and so when the phase of one transmitter is shifted, then the transmitted wave can assume arbitrary polarization states, like from slant polarization to circular to elliptical. And there were 2 horn antennas installed, attached to a power meter, once on the ground and once airborne on a drone. And so these antennas, they were tilted by 45 degrees, and the radar was tuning or was shifting the phase of one transmitter, and then the power was measured with these 2 horn antennas, and the people were looking for a 0 or for a minimum in the power measurement, which is shown here. These are not my plots, and just to explain what the people were doing. So they were looking for a minimum. They found a minimum with the power meter here and a minimum with the drone here. And when they have a minimum in this power measurement, this means that the differential phase on transmission is 180 degrees. And then these people listed down here, they did some calculations, and there are some definitions of the differential phase, and what they came up with is this figure here, minus 110 degrees. And actually this, with both measurements, with the power meter and with the airborne power meter, they came up with the same result. So we tried to do the same thing with our instrument, but with a different method, obviously. So what we did, we sampled a lot of pulses, about 100,000 pulses over 2 minutes. This is an eye diagram of all these peaks 1000 pulses that were transmitted, that we were analyzing. And since we are taking IQ samples, so we have complex samples as shown here, and with these complex samples we can determine the angle between the horizontal and the vertical polarization. So we take 3 samples at the vertical polarization in the middle of the pulse, and 3 samples at the other polarization in the middle of the pulse. And then we do a calculation like this, and this gives us this distance here from here to here, which is the differential phase. But this is the uncorrected differential phase, and uncorrected means this is what we measure in the digital domain. But before the pulses enter the digital domain, there are some analog components like cables or waveguides or strip lines and attenuators, and these components, they also introduce a phase shift, which needs to be determined. And so this is determined by coupling the differential signal into both receivers. And since we know the phase difference of this differential signal, we can use this signal to assess the angle offset. So our instrument is doing this at regular intervals. It's also important that you use high performance phase stable antenna cables that you use. So we use also an expensive antenna, and this antenna is automatically and precisely pointing towards the radar. And if you do all this, then you end up with a time series like this. So this is this 2-minute time series of the phase differential phase angle measurement, and this is like the histogram representation of this time series, and you see the value of minus 104, which is very similar to what the other people have obtained with their measurements. So I think we're quite happy with this result. And this brings me already to the conclusions. So we were investigating 3 different H-band radars. The measurements were done 2 months ago, so it's still very preliminary analysis, but what we can already say is that we found a reasonable agreement in the absolute calibration. Also, data analysis is still ongoing. We found high stability measurements with chill radar. So for me, the most impressive thing actually. And we also found what I just shown, that we can measure the transmit differential phase within the same, or with a good agreement to the alternative methods. There is still a lot to do. As I mentioned, there is this sphere calibration. We have not received the data, but it will be interesting to look to make intercomparisons between the metallic sphere and our data. We have to investigate where these offsets are coming from, especially for the differential reflectivity, and I think we also should repeat these measurements at that C and that S band. Yeah, that's all. I'm very grateful for the support of the people I have listed here at Colorado State University and at the Advanced Radar Research Center in Oklahoma. It was a tremendous effort of all these people. I'm very happy that they provided their facilities, and having said that, I'm at the end of my talk, and thank you very much.
Thank you very much, Marco Cavella. I have a question regarding the spectrum width.
Yes.
I think it was a CSO chill data.
Yep.
And the question is, what was the speed rotation of the CSO chill?
Yeah, I think it was 0.3 degrees per second. So slow. And of course, you're right that actually the spectrum width is a measure of the speed of the antenna as well. But actually, this effect of the antenna, or of the speed of the rotation speed of the antenna, when the antenna rotates that slow, is much lower than the phase noise effect, because the chill radar is a magnetron radar, and magnetron radars, they have larger phase noise than klystrons or solid states. So I think that actually these effects, these are pure instrumental effects.
The chill radar is a klystron radar.
No, that's not. That's true, but the S band of chill is a klystron radar, but the X band of chill is a magnetron radar.